Have you ever stopped to think about why a desert can be scorching hot during the day and then freezing cold at night? Or how you can still get a sunburn on a cloudy day? Well, the answer to both questions and so much more comes down to this really elegant concept called the Earth's energy budget. Today, we're going to follow the sun's energy on its incredible journey from space down to our planet and back out again to see how it shapes, well, everything about our climate.
Okay, so let's start with a question that seems super obvious. Why is it hot at the equator and cold at the poles? I mean, we all just kind of know that, right? But the actual why of it, that takes us on a pretty fascinating journey. We're going to trace a single beam of sunlight and see exactly how the Earth deals with all of that incoming energy. It's a story about angles, reflection, and a surprisingly perfect balancing act. All right, so first things first. Before we can talk about what the Earth does with energy, we have to talk about the energy that actually arrives here from the sun. This is our starting point. Now, there's a cool scientific term for this: insolation. It's basically short for incoming solar radiation. You can think of it as this raw gift of energy from the sun, and it arrives in these short, powerful waves. This is the fuel for our weather, for our oceans, for pretty much all life on Earth. But as you're about to see, not every part of the planet gets the same dose of that gift. So how much energy a particular spot on Earth gets depends on a few different things. The time of day, the season, whether it's cloudy. But the single most important factor, the one that really explains the huge difference between the tropics and the poles, is the angle of the sun's rays. And this, right here, illustrates the whole idea perfectly. Near the equator, sunlight hits the Earth almost straight on. It's like pointing a flashlight directly at a wall. All that energy is concentrated in a small, intense circle. But at the poles, that very same amount of energy comes in at a sharp angle, so it gets spread out over a much larger area. The beam is weaker. That simple difference in angle is everything.
So, if the Earth is constantly being bombarded with all this energy from the sun, you've got to wonder, right? Why doesn't it just keep getting hotter and hotter until it boils? Well, the answer lies in one of the most amazing systems in nature, the planet's heat budget.
To make this super simple, let's just imagine that 100 units of energy from the sun arrive at the very top of our atmosphere. Our mission now is to track every single one of those 100 units and see where it goes. Okay, right off the bat, a huge chunk, 35 of those 100 units, doesn't even get to play the game. It's immediately reflected straight back into space by bright things like clouds or the massive ice sheets at the poles. That energy never even gets a chance to warm our planet. And this reflectivity has a name. It's called albedo. It's a really crucial part of keeping the planet cool. You can think of albedo as Earth's natural sunblock. Without our clouds and ice reflecting all that energy, our planet would be a whole lot warmer. Now, what about the other 65 units that do stick around? This is where it gets really interesting. About 14 of them get absorbed by gases in the atmosphere. But the real powerhouse here is the surface. The land and the oceans absorb the other 51 units. Then, the Earth radiates that energy back upwards. And it's that outgoing energy that does most of the work heating our atmosphere. And that's the whole takeaway here. For every 65 units of energy the Earth's system absorbs, it radiates 65 units right back out to space. The books are perfectly balanced. Income equals expenses. This incredible equilibrium is what has allowed Earth to maintain a relatively stable, life-friendly temperature for millennia. Okay, so we've just established this really important fact. The atmosphere is mostly heated from the ground up, not from the sun down. But how does that heat actually get moved around in the air that we live and breathe in? Well, it's not just one thing. It's actually three processes all working together.
If you remember one thing from this whole explainer, let it be this. The sun's energy comes in as short-wave radiation. Think of it like a quick, high-energy punch that passes mostly through the air and hits the ground. But when the ground radiates that heat back out, it's in the form of long-wave radiation, a slower, gentler wave of heat that the atmosphere is really good at grabbing onto. It's like a giant stovetop warming the air from the bottom up.
The very first step in that process is called conduction. This is super simple. It's just heat transferred through direct contact. The air molecules that are literally touching the warm ground get heated up, just like how the bottom of a pan gets hot when you put it on that stove. So, once that bottom layer of air gets warm, what happens? Hot air rises, right? It becomes less dense, and it starts to float upwards. This vertical movement of heat is called convection. You see this all the time when you boil a pot of water. The hot water from the bottom rises up,
In the atmosphere, these rising currents are what transfer heat from the surface way up into the troposphere.
And finally, number 3 is advection. This is just a fancy term for heat moving horizontally, and we have a much more common name for it: wind. That's all it is. When a warm breeze blows in from the south, that is advection in action, moving heat from one place to another and causing most of our day-to-day changes in weather. All right, we've got the basic physics down, but you know that two places at the same latitude can have totally different climates. So why is that? It's because that initial dose of solar energy is just the starting point. There are a bunch of local factors that then get to stir the pot. This table sums it up nicely. We've talked a lot about latitude, but altitude is also huge. I'm sure you've noticed that as you go up a mountain, it gets colder. That happens at a pretty predictable rate called the normal lapse rate. It's about 6.5 degrees Celsius for every 1,000 meters you go up. That's because the air gets thinner and just can't hold on to heat as well. It's like you're wearing a thinner and thinner blanket the higher you climb. And this one is a really big deal. Land heats up and cools down super fast. Water, on the other hand, takes a really long time to change temperature. That's why coastal cities tend to have pretty moderate weather all year round, while places deep inland, like in the middle of a continent, have these extreme temperature swings between summer and winter. The ocean acts like a giant temperature regulator for the entire planet. So the normal rule we've established is that air gets colder the higher you go, right? But sometimes, in this really fascinating atmospheric twist, that rule just gets completely broken. This whole phenomenon is called a temperature inversion. And yeah, it's exactly what it sounds like. The temperature profile gets flipped upside down. Instead of having warm air near the surface and colder air higher up, you get a layer of really cold air trapped at the ground, right underneath a layer of warmer air. The perfect recipe for an inversion is a long, clear, and calm winter night. The ground just radiates all its heat away into space and gets really, really cold. That, in turn, chills the layer of air right above it. And because cold air is dense, it just sits there. It doesn't want to rise. So you get this stable lid of warm air trapping everything below it. This is exactly why you often see dense fog or pollution just hanging in valleys on those cold, still mornings. So, from the angle of the sun's rays all the way to how the land and sea heat up differently, we've seen this intricate dance of energy that creates the world we know. It is a beautifully balanced system that has kept our planet stable and habitable for eons. And that brings us to one final, really crucial question we should all be thinking about. What happens when we start to tip the scales on that delicate balance?